So, hi everyone. So we're very happy to have Eshwar Ram Arunachaleswaran today as our speaker. So Eshwar is a PhD student at UPenn right now, and he's advised by Sampath Kannan and Anindya De. He's interested in problems in algorithms and complexity, and he has a focus on algorithmic fairness. And so today he's going to talk about our joint work with Sampath and Aaron about pipeline interventions for fairness. So, yeah, take it away, Eshwar.
Yeah, let me just share my screen for
Yep.
some reason. A little glitch. Okay. All right. So here we go. So hi everyone. Thanks very much for turning up for this talk. My name is Eshwar, and this is a talk on our work pipeline interventions. This is joint work with Sampath Kannan, my advisor, Aaron Roth, and Juba, who are all currently at least at Penn. And I want to thank Juba for loaning me his slides. This talk will have a lot of similarities to Juba's talk at ITCS, if you've attended that one. But since I have a little more time, I'll be talking a little more about some hardness of approximation results that are part of this work. All right. So we're going to talk about pipelines because decisions are made along pipelines. So you might have decisions that are affected, at least implicitly, by things that may have happened a long time ago. So for instance, preschools you might go to influence the schools that you get to join, which influence the universities that you get admits to, which in turn influences your job opportunities. And naturally, what happens here is that inequalities creep in at different stages of this pipeline. And these inequalities kind of play with each other. So for instance, if you have disparities, even at the preschool level, for instance, they might turn out to have a lot of compounded impact on the rest of the pipeline and on things as far away as hiring decisions. And what the question that we are really interested in is where and how we should intervene to eliminate or at least try to reduce these disparities. And one thing that's kind of right away there is that intervening just at one point or intervening right at the end of the pipeline may not be sufficient. For instance, if you wanted to improve the hiring prospects of a disadvantaged subpopulation, you might find that just intervening at the final step of the process might be too late to really address the fundamental issues because very few people from your disadvantaged population may be left in your pipeline by that point. In contrast, if you switch things up and try to target your interventions early on in the pipeline, it's kind of hard to see whether it has any concrete effects or long-term effects. At least you want to assure yourselves that whatever you're doing early in the pipeline has some payoff later on in what happens. And what we really want to do is we want to come up with a way to intervene at several levels rather than just picking like a single point to intervene in. And we want to understand how these interventions at different levels affect each other. And using this understanding, we want to design some optimal interventions which happen at different stages of the pipeline with the objective of reducing inequalities across different groups. So our first contribution in this is to come up with a very stylized model, a very stylized formal framework of this problem. And I want to emphasize right away that this is just like a first attempt at trying to draw up a mathematical model on this problem. It's not in and of itself a model that exactly captures what goes on in the real world. It's the first step in trying to understand the problem and trying to bring tools from optimization and computer science to kind of attack this problem. Okay, so what does a setup look like? So we are looking at this layered graph. So you have a graph with a bunch of layers that you see on the screen. And Let's look at the starting layer first. So there are a bunch of nodes at the starting layer denoted by the x's. And the idea is that different starting nodes correspond to different subgroups or different subpopulations. And if you look at every subsequent layer in the graph, each layer is supposed to correspond to a stage of life, or a little less optimistically, a stage in the pipeline. And every node in a layer corresponds to a particular state in that given stage. So for example, the first layer might be the layer corresponding to the preschool stage, and each node may be a particular preschool. And there's something special about our final layer as well. So every node in the final layer has an associated number that captures the quality of that outcome. So you just have like this one number, and a larger number means a better outcome, roughly speaking. Okay. And how do individuals go through this pipeline? So an individual starts at the starting node corresponding to their population. And we have a bunch of stochastic transition matrices. And these matrices govern how an individual walks across this pipeline. So the individual starts at their respective starting node, and in purely stochastic fashion proceeds to a node in the next stage, and so on and so on. And our problem instance basically has a status quo, which is the initial transition matrices between the successive layers. And as you can see, the idea is that this set of models, what kind of opportunities that different groups have. Like for instance, certain groups might have very high probability paths to reward nodes that may not have a large reward. And these would be the disadvantaged populations in our setup. Okay, and what is our model of interventions? So we have a centralized designer who gets to see this entire setup, who gets to see the status quo, how people are moving in this pipeline. And the centralized designer can intervene at any subset of the stages on a set of special edges, which we call the malleable edges. So some edges just can't be changed. Nothing we can do about that. But whatever edges are malleable, the designer can intervene by changing the probabilities on these edges. And the only constraint is that at the end of the changes, the matrices must still be stochastic, in the sense that anybody at, say, layer 1 must move with probability to some node in layer 2. We just get to rearrange the probabilities of moving to different states in layer 2, in the next layer. Of course, nothing comes for free. There are constraints, and the constraint is that there is some cost associated with making any change in these transition probabilities. And we have a maximum budget, and we can only spend as much cost as our maximum budget permits us. And these costs are additive. And to just drop some formal, some notation onto this, we have a cost function C that takes the initial transition matrix M0 sub T as an input and gives us a final transition matrix, which is M sub T, between layers T and T+1, and C is just a function that gives us a number, which is the cost of making this change. We make two assumptions about these functions. The first assumption is that these functions are convex in the input M sub T, and we kind of use this to do some optimization. And the other assumption is that these functions are anti-Lipschitz, which is just a way of saying that any change you make to the initial transition matrix, no matter how small or large, has at least some associated proportional cost. So it's just saying that you don't get to change anything for free at any point, which is like a very natural assumption to make about the cost function. And our constraint just says that let's look at the changes that we make at every layer. The net cost of all these changes added up must be no more than B. So there's something that's slightly, off with the notation here. And then what I mean by that is the way it's set up here, it looks like the same cost function C has to be used for every pair of layers. that need not be the case. We can have very different cost functions in transitioning between preschool and K-12 and K-12s and university. So I think the same notation is also used in our papers, but we actually have a more general model. I just want to make that clear right here. Okay, so what is our main contribution in this setup? Our main contribution is coming up with algorithms for nearly optimal interventions. In particular, what exactly is an intervention? An intervention would be proposing a split of the budget across every pair of successive layers, and a way to use the budget to change the transitions between every successive pairs of layers. And our approach, which I will expound upon in more detail, is based upon first discretizing the space of distributions on each layer, and then using dynamic programming to tie up what happens across all the layers. And one important caveat is about the runtime of these algorithms. So the size of an instance of a pipeline instance has two components to it. One component is the number of layers, and the other component is the maximum width of each layer. And the width of any layer is just defined as the number of nodes in that layer. And as you can see, the number of nodes in the entire pipeline is just the product of the maximum, is upper bounded by the product of the maximum width and the number of layers. And one important caveat is that our algorithms are efficient. In particular, they are polynomial in the number of layers, but they are only efficient when we have a constant layer width. And I'll talk more in more detail about why this is in some sense a necessary assumption in this model. Okay, so what exactly are we optimizing for? There are two broad objectives that we're working with. The first objective is what we call the social welfare, and it has the usual meaning in the sense that we are given the distribution over the starting nodes, which is equivalent to the distribution between different subgroups. And we want, given any individual in the population, we want to maximize the expected reward of this individual. Or if you want to think about it in a slightly different way, you want to maximize the sum of expected rewards over all individuals in the population. And of course, the potential drawback of this objective is that it might ignore disadvantaged subpopulations. So it might just find some low-hanging fruit just to increase the welfare of some small subset of the population, and that would be like a good utilization of budget. But there is a potential of it ignoring disadvantaged subpopulations. And that's why we have a second objective, which is what we call the maximin objective. And the objective just looks to maximize the minimum expected welfare that you can guarantee to every subpopulation. And I'll talk a little more about why these are two fundamentally different objectives a little later. Okay, so let me quickly go over the algorithm to approximately optimize the social welfare. And let's talk about the easy case where there are only two layers in this pipeline. And therefore, there's just a single transition matrix that governs movement from the first layer to the second. We are, of course, given the distribution over the subpopulations, which is the distribution over nodes in the first layer. And every node in the second layer has an associated reward since it's the final layer. And the nice thing about this problem is that you can right away frame this as a convex optimization problem. The objective is just the scalar product of the rewards vector with the resulting distribution on the second layer, which happens when you apply the transition matrix M1 to the starting distribution D. And the only constraint is that M1 should be not very far from M0, 1, which is the initial transition matrix. This, of course, we can do in polynomial time. So this is fantastic. It's an easy case for us.
Can I ask you a question? Sure.
Yes.
So each row in this graph corresponds to one subpopulation. Is that correct?
Not exactly. So the idea is that you're looking at the very first layer, and let's say you have two groups, and you have only two nodes in the first layer, and everybody in the first population starts on the first node, while everybody in the second population starts on the second node. And there might be some different transition functions, going from the first layer to the second, between these two populations. But if you have two individuals arriving at some node in the second layer, it's as if there's no difference between what happens to them.
Yeah, so something also that I want to add up to this is if you want to have a difference between nodes, that, like, imagine you're at layer 3 and you want different populations to have different transitions, you can actually do that through having, you have a duplicate of each node for each subpopulation, so you have a bunch of dummy nodes, like you have a bunch of so for example, node 1 on layer 1 corresponds to a certain level for a certain school or something, and you can have like several replica of that node for different populations, and you can kind of like move the transitions of those replicate nodes together if you have the right cost function, if the cost function has some correlation between those different transitions.
I see. Nice. Thanks. Yeah.
Yeah, so just to kind of clarify, the consequence of what we just discussed is that these values, this distribution D over the penultimate layer, in this case, since it's just a two-layer graph, exactly corresponds to, like D1 is the percentage of the population starting in subgroup 1 and so on. But in general, if you're looking at k-layer graph and you're looking at, say, the distribution of the population on the penultimate layer, this distribution does not have like an immediate relation to the original distribution that split your overall population into subpopulations.
So the first column of this graph corresponds to the original distribution, like those D1 through DW, like you have. And like correct. The rest of the graph may not have any relationship to the subpopulation.
That's correct. Of course, it depends upon these because it's a very we are looking at only the expected values of the distribution on the further layers. But yeah, so just think of D1 as the fraction of population 1, D2 as the fraction of population 2, and so on. And as these transition matrices happen, maybe in some utopian world, everyone just goes to a single node in the very first transition, and the resulting distribution will just be like 1, 0, 0, 0 all over the second layer.
Okay, thanks.
Yeah. Okay. So well, we kind of saw an easy case for maximizing social welfare, and the question is, how do we generalize this when we have k layers? And the approach is to use dynamic programming, working backwards, starting from the final layer. Okay, so now we have the general instance, and now we are looking at again the final transition between the penultimate and the final layer. And if somehow we knew the distribution of the population on the penultimate layer, and we knew the amount of budget that we're going to spend on the final layer, these are dk and d sub k respectively, then we can again resort to the same convex optimization problem that we saw on the last slide. But the problem is that dk now depends upon the interventions that you might have made in the previous layers. So it's not a priori known to us. For that matter, neither is dk. And the idea is to try to do this for all possible values of d sub k, and to kind of so the set of distributions is infinite, so we need to do something to make it finite. And what we do is that we drop an epsilon net on the space of distributions on the penultimate layer, and we can upper bound the size of the net as by 1 over epsilon raised to the power w, where w is the maximum width of any layer, since these are like w dimensional points that we are dropping a net over. And if w is a constant, then this is still a constant number of possibilities that we are going over. And what we're going to do is that we're going to go over all these constant possibilities, solve all the each of these problems, and remember all these solutions. So it's still polynomial time and polynomial space that we're using for this setup. And the more general subproblem we are trying to solve is that we are trying to start at layer T. Once again, we are magically told the starting distribution on layer T, even though we don't know what's happened before layer T. We are also told the budget that's left to us, that's already been used up, and the budget that we can use to the right of layer T. And we want to now solve this problem. The idea is that we split it into two problems. One is the problem of changing the transition matrix between layer T and layer T plus 1. And the changes we make between all the changes we make between layer T plus 1 all the way up to the reward layer. And the reason we really do this is that we have already solved the problem starting at layer T plus 1, since we are working backward in a dynamic programming solution. So the second problem I mentioned has already been solved. And the idea is that once you have solved all the interventions you want to make between layer T plus 1 and the reward layer, you can compute the expected reward at each point at each node in the T plus 1 layer. And you can reduce the first problem to just the same old convex optimization problem that we were solving when we had just the 2-layer instance. We are again going to iterate over all possible distributions of the T plus 1th layer as well, since we have the solutions for all such problems. And we picked the implicit reward vector that performs best for us.
I have another question.
Yeah, sure.
You mentioned this, but rewards are only defined for the last layer. So what is this RT here?
Okay, so let me just explain, going back to our special case, the easy case. So once we solve the case with just 2 layers, we know the final transition matrix M1. Right. Now, once we have the final transition matrix M1, we also know that it implicitly defines an expected reward starting on each of the points in the penultimate layer. Does it make sense? Because at any point X, exactly the final probabilities with which you'll walk to each of these rewards.
But here, like the second layer is your final layer where you have all the rewards.
That's correct.
Okay.
And the idea is that if you have already solved the subproblem starting at layer T plus 1, that essentially means that you have fixed all the transition matrices to the right of layer T plus 1. And as a consequence, you know exactly the reward associated with any point in the T plus 1 layer.
Mm-hmm. Yeah. Okay. Makes sense.
And one more nice thing here is that once you have figured out what you want to do starting at the T layer, you can forget everything you have done at the T plus 1 layer, because you're only going to use the current solution to extend this dynamic programming. And as a consequence, you only need to store a polynomial amount of information at every point of time. And once you go all the way back and you reach the first layer, you no longer have to guess the distribution you're beginning with, because we know the distribution at the first layer. And that will give us an approximately optimal solution for the given starting distribution. One more point to note here is that all this talk has implicitly assumed that we know exactly how to split the budget across the different layers. But again, that's not known a priori. That's our problem to solve. And we use pretty much the same approach, where we just drop a epsilon grid over the budget, and we try every possible budget split at every stage to figure out what the optimal budget split is. And of course, this discretization comes at a cost, but we can show with some simple inequalities that the cost is not prohibitive. We lose an order of epsilon at each step, and in the worst case, order of k epsilon across the k layers. And as for computational efficiency, we are only looking at a constant number of possibilities, and we are solving a polynomially sized convex program at each step. And we're only doing this k times. So as a consequence, our running time is polynomial, the space usage is polynomial. So the entire run, it's an efficient algorithm. And all of this was only for the social welfare, but you can extend it very easily to the maximum welfare. Instead of keeping track of only the distribution of the entire population at the teeth layer, we can do something a little more fine-grained and keep track of what happened to somebody starting from population 1 in the teeth layer. So this just increases the number of possibilities we are looking at by the number of subgroups, which is upper bounded by W, the width, and it's also a constant. So we have only a constant blow up in size everywhere. And as for the optimization program, we are just going to add a subgroup number of constraints, where instead of just maximizing the global social welfare, we are trying to maximize the minimum value that is larger than everybody's social welfare. Sorry, that everybody's welfare is larger than. So pretty much the same approach with some little more work can be extended to the maximum objective.
And we have a question in the chat. Nikhil is asking, is the search over the budget partition a grid search, or is it possible to find a faster approach?
Well, we have done a grid search, and you may be able to do something a little more intelligent by looking at the graph as a whole. It's not clear. It's not clear that the grid search is the best possible way to do it. That's the answer I can give you to that. Okay. So that was the algorithm.
We have another question. But also, I just want to add to this. It's not clear that the grid search is the best thing you can do, but you will still, I mean, you're going to get to this Eshwar, but like we still have hardness results, which is that the problem is hard if W is not a constant factor. So essentially, you're not going to be able to improve that too much. And so I think Milan has a question.
Yeah, I was just wondering. So the maximum objective is taken over the initial groups. Is that right?
That's correct.
Okay, so then is it right that the initial groups have kind of like a different interpretation than all of the other sets of groups in the model? Like I should think of them as like protected groups or something, whereas the other ones are just sort of kind of intermediate stages where people end up.
Yeah.
Okay.
Yeah.
Cool.
Yeah. The first layer is kind of special in that way. Okay. So I'm going to talk a little about the reason why we were working with a constant width graph, a constant width pipeline. So we were having an algorithm for any number of layers and a constant width pipeline. So it's a natural question to ask: can we flip this around and come up with an efficient algorithm when we have any number of nodes in a given layer, but a constant number of layers? And the answer to that is a no. Basically, we have a result that says that coming up with a multiplicative 2 approx for maximum welfare is hard even for a constant number of layers. And this is via a reduction from the gap version of the vertex cover problem. So quickly to describe the vertex cover problem, you're given a graph with vertices and edges. And a vertex cover is just a subset of the vertices such that every edge is incident on at least one vertex in the subset. So trivially, all the vertices in the graph are a vertex cover, but we want to find as small a vertex cover as possible. And the classical addition problem is, given the graph and some variable kappa, a number kappa, we want to figure out whether the graph has a vertex cover of size kappa or not. This problem is known to be NP-hard. But I'm going to talk about an easier version of this problem. We just want to figure out if there is a vertex cover of size kappa, or whether the graph has no small vertex cover. Like either it has a small vertex cover, or the smallest vertex cover is much larger than kappa. the slide has a small mistake on it. There's a proof by Dinur and Safra that says that there is no polynomial time for the gap version of vertex cover unless P is equal to NP. So essentially, if you can solve this problem, we show that P is equal to NP. And we are going to show that if we can come up with the two approximations for vertex cover, we can actually solve this gap version of vertex cover in polynomial time. So let me quickly describe the reduction. So we take the given graph G, and for every edge in the graph, you're going to add a node in the first layer of our pipeline. So the edges in the original graph are going to look like the subgroups in our pipeline. And for every vertex in the original graph, you're going to add k copies of that vertex as nodes in successive layers. So if you had a graph U, sorry, if you had a vertex U in the original graph, you're going to have nodes U2 in the second layer, U3 in the second layer, U4 in the third layer, and so on. And additionally, the only edges that are of interest to us are shown on the screen. So every edge in every node in the first layer has two edges of each with initial probability half, going to the vertices which is incident on in the original graph. And we have a path corresponding to every vertex in the original graph. It consists of edges going from U2 to U3 to U4, all the way until the final layer, which has two vertices. And this path ends at the vertex with reward 1. And each vertex has some initial probability epsilon. The other edges of interest are these dotted lines that you see on the screen. Think of them as just like a leftover probability edges. All of them are going to some dummy X nodes in each of these layers from the third until the k+1th layer. And once you go on a dotted edge, you will essentially go to the 0 reward node with probability 1. And let me tell you what the malleable edges are. The only malleable edges are all the path edges and all the dotted edges. So you cannot change any of the edges in the first transition between the first and the second layer. And you cannot change any of the outward transitions from the X nodes. So if all of this is really complicated, just focus on the path edges. Those are the only places where interesting things happen. So I'm going to skip some of these intuition slides since I'm doing reasonably well on time. Okay. And additionally, okay, so now we have this pipeline instance, and I need to tell you what the budget for this pipeline instance is. The budget is some complicated looking figure, but I'll break it down. So it's 2k times kappa times epsilon, where k is the number of layers, kappa is the vertex cover size that we are looking for, and epsilon is just the epsilon that we already have on this graph. And all costs for the malleable edges are linear with slope 1. That just means that if you want to change any of the transition probabilities by delta, the associated cost is delta. And what I want you to note is that the initial welfare of every node in the first layer is going to be epsilon to the power k. This is because every node in the second layer has a path of probability epsilon to the power k to the 1 reward node, and the rest of the probability goes to the 0 node. And every node in the first layer is connected half and half to 2 epsilon to the power k reward nodes in the second layer. And I'm going to define this threshold T, which is the initial welfare multiplied by a very large number, which is like roughly 2 to the power k here. Okay, so what is the main technical lemma that we kind of use to do this reduction? We are going to show that if there is no vertex cover of size kappa, then the maximum value is sufficiently large, at least twice this threshold. And we are going to show that if there is no vertex cover of size 1.3 times kappa, the vertex cover, even the smallest vertex cover is reasonably large, then we are going to show that the maximum value is correspondingly small. In particular, it's strictly less than T. And what I want you to note is that this right away tells you that any two approximation algorithm for maximum welfare would be able to differentiate between these two cases. All you'd need to do is you just run the algorithm, compute the maximum welfare, And if the welfare is less than t, then you say the vertex cover must be very large. If the welfare is greater than or equal to t, then you know that the vertex cover is going to be fairly small. Okay, so let me try to walk you through the two directions of this proof. The first is the easier direction. So there is a small vertex cover, then the maximum value is reasonably large. And the proof is by showing a candidate split of the budget that actually achieves a good maximum value. So if you have a small vertex cover, what you'll do is that you'll pick each vertex in the vertex cover, look at the corresponding path for that vertex, and increase the probability on each edge by epsilon. And again, I want to just note that increasing the probability by epsilon means that you take away epsilon probability from the dotted edge and add epsilon probability to the path edge, which is going to have a total cost of 2 epsilon. That's why there's a factor 2 in the budget. So you use up the budget to improve all the paths corresponding to the vertices in this small vertex cover. And the idea is that this is going to drastically improve the welfare by a factor of 2 to the power k, because by definition, a vertex cover covers every edge. So if you look at any node in the first layer, it's going to be connected by a half probability edge to at least one vertex in the vertex cover. And we know that vertices in the vertex cover have like a 2 to the power k times the original welfare they were getting. And as a consequence, the welfare that's guaranteed to every node in the first layer is pretty large. The other direction is a little trickier. So I think I only have time to give you like some intuition about it. So it's a proof by contradiction. So let's say that we are given that there is no small vertex cover. Any vertex cover has to be at least as large as 1.3 times kappa. Let's assume that the maximum value is still larger than t. And the idea is that we are going to look at this maximum, the split of budget that achieves this maximum value. And we are going to construct a small vertex cover based on the split. Okay. And in particular, if you look at the budget spent on each path, you can denote it by, we are going to just say it's some 2k epsilon times AV, where A sub V is some variable. What does it mean? So it essentially tells you that, look, on the path corresponding to U, we are going to spend at most 2k epsilon times AU amount of budget on it. And we can show using some simple inequalities that, let's, instead of U, just think of V. The increase in welfare is maximal when you equally distribute the budget across every edge on this path. And this is what the expression looks like. I know it's a lot to deal with, but we don't really need to look very closely at this expression because I'll talk you through what its consequences are. And basically, after doing this, if you write out all the constraints, we get something that looks like this. What does it mean? Okay. So first of all, we have a constraint that corresponds to every node in the first stage having a reasonably large welfare, which is like 2 to the power k times epsilon to the power k. And since this is a maximum objective, we are guaranteed this for every node in the first layer and consequently every edge in the original graph. But we also know that the total budget is upper bounded by 2k times kappa times epsilon. So if you add up all the budget spends over all the paths, the sum of the AV variables is going to be at most kappa. Now, what this should remind you of is the linear program for vertex cover, which you can round to get a 2 approximation. And we are going to use a very similar idea and round to get a 1.22 approximation. And like I promised, the number of layers is going to be a constant. In fact, it's a very small constant. It's 15. And the idea is that if you look at the equation corresponding to every edge, at least one of these quantities has to be half the right-hand side. It's going to be 2 to the power 13. And as a consequence, at least one of these 1 plus AUs must be 1.823, which is just the 15th root of 2 to the power 13. And therefore, the rounding idea is to just select the edge, the vertex V, if A sub V is at least 0.823. And it's very, very similar to rounding the linear program for the vertex cover problem. And you can use the exact similar arguments to show that this is in fact a vertex cover. And this is going to give you a vertex cover of 1 over 0.823 times kappa, which is 1.22. And this is a contradiction because we started with the hypothesis that there is no vertex cover smaller than 1.3 times kappa. And therefore our assumption was wrong, and the maximum value must be smaller than p. So in conclusion, what we're getting here is that two multiplicative two approximation algorithm for maximum welfare. It's not NP hard, but it's not going to happen in polynomial time unless p is equal to NP. I guess it's NP hard, I'm not sure now. And there's nothing special about the factor 2 here. Even if you gave me a fact, even if you asked me to come up with a factor 1000 approx, I could still construct a hard instance with a constant number of layers that would rule out even 1000 multiplicative approx for maximum welfare. And we can also massage this to show that additive approximations also can't be done in polynomial time. Personally, I kind of find this cool because we are getting a insight into a modeling constraint from a complexity theoretic result, which I kind of find cool. And yeah, okay, so what's left to go over? Okay, so we have some results about the price of fairness. So what is the price of fairness? It's the worst case ratio of the optimal social welfare to the social welfare of the maximum solution. So you're going to go over all instances. You're going to look at this ratio between the social welfare when you're just optimizing for social welfare and the social welfare value of the smallest possible social welfare value of the maximum optimal solution. And you're picking the instance that maximizes this ratio to get this value, which is the price of fairness. And we analyze the price of fairness for a relatively simple case when we again have linear cost functions with slope 1. And you can see the results on the screen. Some of it corresponds to our intuition. So for instance, if the budget B is sufficiently large, then the price of fairness is 1. There is no difference between optimizing for social welfare and optimizing the maximum solution. And as you can imagine, this is because this is kind of a utopian world where you have enough budget to spend on making sure that everybody gets a really large amount of welfare. But when the amount of budget is a more realistically small value, not realistic, it's just a really small value, the price of welfare is going to be, can be as bad as the width of the pipeline, which in turn corresponds to the number of populations that we have. And for intermediate values of the budget, the price of fairness is going to become smaller and smaller as the budget grows larger and larger. So yeah, like these are all instances which kind of illustrate when the instances that generate these values illustrate when optimizing social welfare is a fundamentally different problem from optimizing the maximum welfare. Okay, that brings me to the very last thing I want to talk about, which are future directions. So again, what I wish to emphasize is that everything we have is only a first step towards tackling this problem. It's a very stylized model with a lot of simplifying assumptions. And of course, in practice, we have to think of ways to improve this model. And these are some not exhaustive, it's a non-exhaustive list of things that we can do to make this model more realistic. So one thing is that interventions made early on in the pipeline might have a direct impact rather than just an implicit impact on what happens in the future layers. In particular, if you're improving access to good preschools, you might implicitly be improving things that happen between schools and universities, which is not something we are modeled for. And all our results assume that the same transition matrices apply for people, for individuals coming in from different populations. So that's like saying that, to everybody who lands at Harvard is going to have the exact same prospects, or everybody who lands at some school is going to have the exact same prospects. And we can think of ways to generalize this by saying that maybe we need to have different sets of transition matrices and ask ourselves, can we replicate our results when these transition matrices are similar, different? What are the things that we can do? Another kind of modeling change, which I personally find very exciting and which we did think about for a bit, is what happens if these transitions are not necessarily stochastic, but they involve strategic elements based on some agency that you give to individuals. So perhaps it's not just a flip of a coin that decides what happens to an individual at any stage. Maybe the individual makes some decisions based on some information available to the individual. And we have to account for these strategic elements as well while designing our interventions. So that's one possible way in which we can completely change our understanding of how individuals proceed across this pipeline. Another element that it would be great if you could add it are feedback loops. So by design, our graph was acyclic. Once you moved from left to right, you could never come back to the point where you started at. Or nothing that happens in the future affects what happens in the past. But we know that that's not necessarily true. There are feedback loops, and it would be great if you could come up with a nice model that captured this element as well. And of course, our reward model was assumed that rewards are just a one-dimensional quantity. They are just a number, and which is kind of reductionist. And we even assume that everyone values the same outcomes equally, which may not be the case even within the same group. So that's again a direction that we can take this model to. And final question is, we have assumed that we have had a centralized designer which designs these interventions and has the complete freedom to spend budget as the designer sees fit. But we might ask ourselves, what happens if we have multiple designers intervening at different points with different kind of budget constraints on each of them? So these are all the things I wanted to talk about. I hope you found it interesting, and I hope that you can find some interesting problems building upon some of the ideas here. And thank you again for listening.
So yeah, do we have any questions? Also, yeah, thanks for the great talk, Eshwar.
There is one question in the chat. Farzan is asking, have you thought about experiment design on any real data?
No, we have not thought about experimental designs on any real data. No.
Though, to be fair, Nikhil and I were just chatting about this in the chat like half an hour ago. So yeah. So now we thought about it.
So relatedly, there must be literature on, natural experiments where something changed early in the pipeline and how that affected the outcomes of, students who were placed in some, school outside their neighborhood or whatever. Like there must be some literature in econometrics around those questions, right? Do you know?
Yeah, we haven't really looked into it, but yeah, I definitely imagine so. Yeah, that would. It's not something that we have factored in, but I'm sure there must be a way of improving this model to include, the observations that have been made about these spin-off effects of what happens early on.
So presumably, like all this work around different education styles in, kindergarten or whatever, right? there must be some analysis of, like different methods for how to treat these like this kindergarten kids. How that affects their future outcomes, right? There must be some work measuring this type of things.
Right. Yeah.
Right,
Yeah,
and like that. Oh, sorry.
Yeah, go on.
I was just gonna say that'd be like real interesting to incorporate. So like the way I'm thinking about this is like it's kind of like complementary to what we're doing, right? Because our model is just very stylized, and we're just saying, imagine given the transition matrices and given the cost, what do I do with this? Here is the algorithmic part. We haven't at all looked at what you actually plug in this pipeline. And I think like what you're suggesting would be a really good way of doing this.
Yeah, and presumably, I guess your work also adds an extra component to that, which is like considering combinatorial interventions, right? Rather than
right.
Focusing on certain part of the pipeline. This is related also to the question in the chat, experiments without pipeline or natural experiments that occurred for whatever reason in a combinatorial way, which is what your work is motivating.
Yeah, no, I completely agree.
Yeah. I imagine our model, those interventions would look like a tree that you're adding on, and those are like a discrete set of trees that you can, because every change you make, for instance, with the different styles of kindergarten education, for instance, is going to affect every consequent node that is going out of those particular nodes.
Well, I guess, do we have any other question, or should we just call it a day? Well, it looks like we don't have any questions. So yeah, thanks once again for coming, everyone. Thanks, Eshwar, for giving the talk. It was great. And see you all in 2 weeks. Probably won't be a talk next week. Yeah. See you.